Hi, welcome. I'm going to be talking about periodic trends in ionic radii. In an earlier video, I had mentioned this, that if you have a cation, the atomic radius of the ion is smaller than the atom. That's because, and this shows it pretty well here for sodium, to become the ion, I lose that 3s electron. My outer electron is now in n equals 2, which is going to make it smaller. For anions, the atomic radius of the ion is bigger. That's because we've added electrons, and those electrons cause more repulsion. They push out, so that energy level pushes out a little bit to accommodate that repulsion, and the radius gets larger. Now, what I want to do in this video is expand that a little bit and talk about isoelectronic series of ions and the trends in those. Now, I'm going to talk about this proton-electron ratio in a minute, but what I'd prefer to do is this. I want to look at ions that have the same electron configuration. So let's take, for instance, aluminum ion, the sodium ion, and the fluoride ion. All have the same electron configuration. We would say those are isoelectronic. They have the exact same electron configuration as, I hope that's neon. I should know that, but it's not coming to me right now. I hope that's neon. Well, let's compare them one to another. What I like to do, so this is the sodium ion, this is the aluminum 3+ ion, and this is the fluoride ion. Always compare. This gives you something to wrap your mind around and start processing the explanation at the atomic and ionic level. So you want to compare N, your outer energy level, and Z. They all have the same number of electrons. So we can't talk about repulsive forces here. That's not going to work because they all have 10 electrons. So we need to be looking at attractive forces. You notice here that all of these would end at n equals 2. The fluoride ion has the exact same electron configuration. So they all have n equals 2. That's not going to help us so much. So let's now move on to the next step. Let's compare their nuclear charge. We have 9 for fluorine, or excuse me, I put that in the wrong place, sorry. I have 9 for fluorine, I have 11 for sodium, and I have 13 for aluminum. Now bear in mind, and this is where thinking about it as a ratio can help, we're talking about the same 10 electrons, same number of electrons. Well, if I increase my nuclear charge, I'll increase the attractive forces and I'll decrease the radius. So that's what's being shown here. As you increase your proton to electron ratio, you decrease your radius. So let's look at this picture I snagged. We've got fluorine with 71. Remember, anions become bigger because of that repulsion. It's 119. We've got the sodium atom at 116. Excuse me, that's a sodium ion, forgive me. They had it backwards on here. The sodium atom is 154. The sodium ion is smaller. Cations are smaller than the atom. Here's the atom. Cations are smaller than the atom. So those numbers verify the general principle I mentioned. Now, let's take a look at these compared one to another. So we've got the fluoride ion was 71. So this was 71 for its radius. The sodium was 116 and the aluminum is 68. So you see our predictions did, no, I grabbed the wrong one here. Darn it, Dena. Oh, Dena moment. I noticed my pattern wasn't going the way I wanted. Fluoride is 119. The sodium ion is 116. The aluminum ion is 68. So that follows our pattern of our proton-electron ratio. But you really need to get the heart of it, that it's really about that increased Q, that increased Q positive in Coulomb's law means increased attraction. Phew, that was a tough one. Thanks for hanging out with me and getting through that. I appreciate your time.